This is a silicone wafer. Now, besides my fingerprints, on one side you have a shiny mirror-like surface. On the other side, you have a etching side with all the integrated circuits. In this video, I'm going to show you how you can point a SWIR camera on the unetched smooth side and see through the wafer to inspect the integrated circuit side using our Triton2 SWIR camera featuring Sony's IMX992 5.2 megapixel SenSWIR sensor. Let's get started.
Here's another quick look at the mirror-like blank side of our wafer. Our eyes and the camera I'm using to film this video only sees just that, a smooth reflection. Flipped over, we can see the side with the tiny integrated circuits, or ICs, etched into the silicone wafer. So in order to achieve our goal, getting the right hardware is key for this demo. The three key hardware components we're using will be a Triton2 5.2 megapixel SWIR camera, the TRT053S WC featuring Sony's IMX992 SenSWIR Sensor, Tamron's SWIR 12mm lens, and Smart Vision's RMX140 ring light with 1550 nanometer wavelength output. Note that this ring light has dual wavelength output, but we'll just be using the 1550 nanometer wavelength. We'll set up our components on our breadboard, connect the lens, connect and power the camera using our M12 PoE Ethernet cable, and attach the lights. For the light, we'll aim it against the wall to diffuse the light, or else it'll be too harsh and glaring if we point it directly at the wafer. And that's basically it. Of course, it's not the prettiest of layouts, but the fundamentals are there, where the 1550 nanometer wavelength light will be absorbed at different levels through the IC etched layer, and whatever passes through will be focused by the SWIR lens and detected by the Triton2 camera. Once the SWIR camera is powered, we'll launch Arena View and enable the camera to start streaming. I'll grab our first wafer. Here you can see the IC etched side, and flipped over, the smooth blank side. Well, once we place the wafer in between our clips, all that's left is to focus the camera and tweak the exposure. And there you have it. We can see the IC side through the blank side. Now before we take a look at the next wafer, I want to take a quick moment to compare this second-gen SenSWIR sensor to the highest resolution 1.3 megapixel first-gen SenSWIR sensor. Placing the two cameras side by side, at the same distance from the wafer and using the same lenses, we can image a larger area thanks to its 2560 by 2048 pixel resolution. We can also see more details when trying to image the same area compared to the 1.3 megapixel SenSWIR sensor. Alright, back to the wafers. Let's try the other one. Same thing, we'll place the blank side towards the camera and there you go. We're able to see the etched IC side. We just need to focus the lens to get as sharp of an image as possible. As mentioned earlier, the light we're using is outputting 1550 nanometer wavelength. Different wavelengths will highlight different layers of the wafer, so your results will differ depending on the wavelengths you try. Also, when you turn on a SWIR light, it might seem that this light isn't outputting any light, but it's just that we can't see it, as it is indeed outputting SWIR light. One of the benefits of placing the camera facing the blank side of a wafer to inspect the etch side is that it frees up the other side for other manufacturing components. In other words, the camera isn't competing for space, allowing you more flexibility in your wafer inspection design. Well, that's it for this quick video. Thanks so much for watching and stay lucid.